RAMKUMARI from KSR College of Arts and Science for Women, Department of Mathematics. Now we see the functional analysis, Unit 1 and Unit 2. The aim of this course, functional analysis, is to introduce the students the key ideas of functional analysis. It should be noted that only search the surface of this vast area in this course. We discussed normed linear spaces, Hilbert spaces, Banach spaces, and etc. Now let us see the definition of normed linear space. Let X be a vector space over entire scalar field R of real number or the scalar field C of complex numbers. Suppose we have a function norm from x to 0 comma infinity such that norm x equal to 0 if and only if x equal to 0. Norm x plus y less than or equal to norm x plus norm y. Norm alpha x equal to modulus alpha into norm x for all scalars alpha and vector x. We call x comma norm a normed linear space. Property 2 is called as the triangular inequality, and property 3 is referred to as homogeneity. The reverse triangle inequality is norm x plus y greater than or equal to norm x minus norm y. Next we see the definition of Banach space. A Banach space is a complete normed linear space. The important results discussed in Banach spaces are: every normed linear space is a linear space, every convergent sequence is a Cauchy sequence in a metric space, norm is a continuous function. Then next we see the important theorem named theorem Hahn-Banach theorem. Hahn-Banach theorem, let X be a real linear space and let P be a sublinear function or functional on X. If F is a real linear functional which is defined on a subsequence Z on X satisfying f of x less than or equal to P of x for all x belongs to M, then there exists a real linear functional f on x such that f by z equal to f and f of x less than or equal to P of x for every x belongs to x. Then we see the Hahn-Banach theorem for normed linear spaces. Let X be a normed linear space over the field K and Z be a subsequence of X. Then for every bounded linear functional f on Z, there exists a bounded linear functional f bar on X such that f by Z equal to f and norm f bar equal to norm f into Z, where norm f bar x equal to supremum of modulus f of x bar and norm f into Z equal to supremum of modulus f of x. Some applications of Hahn-Banach theorem also discussed, that is norm f equal to 1, f bar of x naught equal to norm x naught. Next we see the important corollary of Hahn-Banach theorem. Let X be a normed linear space over the field K and x1 and x2 be a distinct points on X. Then there exists f bar belongs to x1 such that f of x1 not equal to f of x2. Next we see the conditions for the completeness in open mapping is essential. Let us see the example and an inverse mapping theorem. Let X and Y be Banach spaces and T from X to Y be a bounded linear operator. If T is bijective, then T inverse is also a bounded linear operator. Next we see the important concept Hilbert space. The definition of Hilbert space is: let X be a linear space over the complex field C and inner product on X is a function x cross x to C which satisfies the following conditions. First one is inner product alpha x comma beta y comma z equal to alpha into x z for all x y belongs to x and beta belongs to C. And then second one is inner product x y bar equal to yx. Then third one is symmetry. A complex inner product space X is a linear space over C with inner product defined on X. Definition of Hilbert space is: a complete inner product space is termed as Hilbert space. Then we see the closed linear operator. The definition of closed linear operator is: let X and Y be normed spaces and T from D of T to X by linear operator with domain determine d of t contained in X, then T is called closed linear operator. If its graph g of t equal to f of x comma y belongs to d of t, y equal to t of x is closed in the normed spaces, and its definition is as usual. Next we see the theorem. Let x and y be a normed spaces and t from d of t to x be a linear operator where d of t contained in x, then t is closed, and if and only if it has the following property. If t xn tends to x where x belongs to d of t and t of xn equal to, then x belongs to d of t, and if tx equal to y. And here we see the Hilbert spaces, Banach spaces, and the important properties in Banach spaces.